Now let's try to calculate the field due to a straight conductor which is placed along z axis and carries a current I. Okay, this yellow shaded straight wire is placed along z axis and it is carrying a current I. Okay, now let's take a small portion in this conductor, that is the red shaded region. Okay, and the length of this is dl. Okay, and it is having a size dz. D means differential, that is small size. Okay, now this point makes a distance r with the point p, and we are going to measure the field intensity due to this conductor at point P. Okay, so as per Biot-Savart law, the field density dH vector is IDL cross R divided by 4 pi R cube. Here, the small current element, okay, dl. Okay, we need this dl, we need this R vector and R cube. I is the current through the conductor. Okay, let's take this one as constant. Okay, so we need dl and r to find dh. Okay, so here first let's take the dl means differential length. Okay, the current conductor is along z axis, so this dl is having a direction az, along direction az, and the size is small in z, so dz. So dl is az into dz. Now let's calculate r. Okay, so in general, suppose you are having a vector like this, say let's a, another vector like this b, then if you the resultant vector of these two is addition of these two vectors is r. Okay, r vector is a plus b. Okay, here instead of a we are having minus az vector, the vector is upward. Okay, minus az vector. Okay, here this is az vector. Okay, but here we are having negative, so minus az, and that along this is a row vector and r vector. So you may write the r vector is minus the length z and vector along z is az plus row a row vector. Okay, so r vector is row a row minus zaz. Okay, and you have to now let's substitute this dl and r here. Okay, here we need to calculate dl cross r. So dl cross r is dz az. Okay, dl is dz az cross r is row a row minus z az. Okay, so in cross product we are having a row a pi az. Okay, we are having three vectors in cylindrical coordinates. If you take cross product of a row and a pi, you will get az. Similarly, az cross a row will give a pi. Okay, so the first two will give row into dz, az cross a row, that is a pi, minus az cross az will be 0. So you will have dl cross r is row dz a pi, and here from this you can calculate the magnitude of vector r, that is rho square plus 0 plus z square. So you will have r is square root of rho square plus z square. Okay, now let's substitute this value in the equation 1. So you will get dz is I by 4 pi rho dz a pi divided by r cube. Here r cube is rho square plus z square power 3 by 2 a pi, and here this one involves dz, and the same term appears in the denominator also. Okay, so it's more complex to integrate. So let's try to change the integration variable from z to another variable, say alpha. Okay, so for that let's first consider this triangle OLP. In this triangle, right angle triangle, If you apply Pythagoras theorem, then you will get r square is rho square plus z square, and if the angle between z and the r vector is alpha, means sin alpha is rho by r. So r is rho cosecant alpha. Okay, r square is rho square plus z square, and r is rho cosecant alpha. Similarly, you can get tan alpha. Tan alpha is equal to rho by z, and z is tan alpha is rho by z, so z is rho cot alpha. Okay, and if you integrate, if you differentiate this equation with respect to alpha, then you will get dz by d alpha is rho cot is minus cosecant square alpha. Okay, so from this you can get dz is minus rho cosecant square alpha d alpha. Okay, now using dz r, okay, and z, equation 4, in equation 4 just substitute dz, and this one is r, right? Just substitute those values, you will get minus I by 4 pi integral alpha 1 to alpha to the limits alpha 1 to alpha 2 instead of uh, 0 to z. Okay, uh, where we are having alpha 1 to alpha 2, already a rho is there. For the dz you are having rho cosecant square alpha, so you will have rho square cosecant square alpha d alpha divided by 4 pi, this one is r cube. Okay, this one is r cube. Okay, so what you will have, r is rho cosecant square alpha. Okay, r is rho cosecant alpha, right? Rho cosecant alpha. Okay, so what you will have, this one is r, so here you are having r cube, so you'll have rho cube cosecant cube alpha a pi. Okay, now you can cancel two rows and two cosecants, so you will have minus I by 4 pi rho, just bring the row outside. So 1 by cosecant alpha is sin alpha, so integral alpha 1 to alpha 2 sin alpha d alpha a pi, so I by 4 pi rho minus cos alpha integral alpha limits alpha 1 to alpha 2 a pi. So if you apply the limits, then you will get h vector is I by 4 pi rho cos alpha 2 minus cos alpha 1 a pi. Here alpha 1 and alpha 2 are the inclination angles at point A and point B. Okay, this expression is applicable as long as the conductor is straight, and h vector is always along a pi irrespective of the length and observation point P. Okay, the point may be anywhere, but the h vector is around the conductor, around the conductor. Okay, so if you are having a straight conductor, okay, the field will be around this. You will have fields encircling this conductor. Okay, so at any point this is encircling the conductor, that is along a pi vector. In this, let's have some special case. When the conductor is semi-infinite with respect to point P, I mean A at origin and B at infinite, means then alpha 1 is 90 degree, alpha 2 is 0 degrees. At the time, if you supply alpha 1 is 90 and alpha 2 is 0, then this one becomes h vector is I by 4 pi rho a pi vector. And the special case 2, and the conductor is infinite in length, okay, A will be at minus infinite, B will be at plus infinite. At the time alpha 1 is 180, alpha 2 is 0, so h vector will be I by 2 pi rho. Okay, so from this you can tell, from this equation you can tell the magnetic field is proportional to current, that is I. Okay, and inversely proportional to the distance rho, I mean the point from the conductor to point distance is rho. Okay, so you will have inversely proportional with rho. Okay, so H hat is I by 2 pi rho A pi vector. Okay, and this magnetic field H is tangential to the concentric circle around the conductor and follows right angle